In Unit 3, we're going to discuss rational expressions. Subunit 3.1 is all about simplifying, multiplying, and dividing rational expressions. So the objective is to be able to do all three of those things. And the essential question is, how is factoring used to simplify, multiply, or divide rationals? A rational expression can be written in the form P over Q, where P and Q are both polynomials, and Q is not 0. So here are three examples of polynomials. They are all rational expressions because we have both a numerator and a denominator that are polynomials. The most complicated one for students to understand is the far right, 3x squared over 4. But 4 is indeed a polynomial. It's actually a constant monomial. So to simplify a rational expression means that we need to write it in the lowest or simplest of forms. Therefore, we need to factor out the numerator and the denominator and cancel out common factors that are present in both the numerator and the denominator. In the top left example, we have 7x plus 35 over x squared plus 5x. What's the GCF of the numerator? And what's the GCF of the denominator? Go ahead and factor those out. You should have gotten 7x plus 5 over x plus 5. Notice that there's an x plus 5 term in both the numerator and the denominator, and therefore those can cancel, leaving us with our answer of 7 over x. In the bottom left example, what do you notice that's different between the numerator and the denominator? Because I see a 7 and I see a y, but what's the difference? In the numerator, 7 is positive, and in the denominator, it's negative. Whereas in the numerator, the y is negative, and in the denominator, it's positive. So the difference between the numerator and the denominator is a factor of -1. Therefore, I can factor out a factor of -1, making my 7 a -7 and my -y a positive y. Some rearrangements makes it easier to see that we have a y minus 7 term in the top and bottom, and those can cancel, leaving us with our answer of -1. In the rightmost example, it gets slightly more complicated because both the numerator and the denominator require factoring. Now, for our purposes, we're going to go ahead and continue to use either our magic X, our reverse box, or grouping. However, once you get a little bit better at factoring, you'll notice that when the a value is 1, it's relatively simple to figure out what multiplies to -4 and adds to 3, or what multiplies to -20 and adds to -1. We rewrite our polynomial expression in the numerator as x plus 4 over times x minus 1 over our polynomial expression in the denominator of x plus 4 and x minus 5. We notice there's an x plus 4 in both the numerator and the denominator, so those cancel each other out, leaving us with our answer of x minus 1 over x minus 5. This is the most challenging simplification problem yet. Is there a GCF on the top and is there a GCF on the bottom? Go ahead and take those out now. In the top, all terms have a factor of 3 as well as an x, so we're going to take out a 3x from all three terms, leaving us with x squared plus 14x plus 48. In the denominator, both 5x and 40 have a factor of 5. Taking that out, we have 5 times x plus 8. We then need to factor the top using either our magic X, reverse box, or grouping to get us a new function of 3x times x plus 6, x plus 8, all over 5 times x plus 8. Notice that there is a x plus 8 term in the top and bottom, and those cancel, leaving us with our answer of 3x times x plus 6 over 5. To multiply rational expressions, we need to multiply straight across. This is the exact same process as we use for simple fractions. If I ask you to multiply 2/3 times 4/5, you would multiply 2 times 4 and 3 times 5 to get your answer of 8/15. The same is true for rational expressions. X cubed times y squared, all over 4y times x. The only thing that we need to add here is that we can simplify this fraction by using our exponent rules to eliminate an x from both the numerator and the denominator, as well as a y from both the numerator and denominator, leaving us with an answer of x squared y all over 4. Here are a couple other examples. 6x squared times 5x gives us 30x cubed, over 10x cubed times 12 is 120x cubed. The x cubes cancel in both the numerator and the denominator, leaving us with 30 over 120. A handy trick for 30 over 120 is they both have at least one zero, so I can cancel out the zero, leaving me with 3/12. 3/12 I remember as being 1/4, so I can simplify it more quickly. However, if you have a calculator, you can always plug in 30 over 120, and again, you would get the decimal form of 1/4 being 0.25. In the bottom example, we are again multiplying, so I'm going to go ahead and expand m minus 9 squared to be m minus 9 times m minus 9. And I'm going to go ahead and take out the GCF of the right fraction in the denominator because both those terms have a factor of m. So I can rewrite it as such, and therefore when I combine my terms in the numerator and the denominator, I notice that both the numerator and denominator contain an m minus n, and they both contain an m. So I can cancel both, leaving me with my answer of m minus n over m plus n. For division of rational expressions, again, it is the same process as for simple fractions. First, though, we would need to factor out the numerator and the denominator, and then multiply by the reciprocal, and lastly, simplify by canceling out common factors. It's easy to remember division as keep, change, flip. I realize I wrote flip, but it is indeed flip. 2/3 divided by 4/5 is 2/3 times 5/4, which is the same thing as 10/12. That can be simplified to 5/6. X cubed over 4y divided by y squared over x becomes x cubed times x and 4y times y squared, leaving me with x cubed over 4y cubed. X plus 3 times x plus 3 over 5 times 25 over 5x plus 3 is the step that we would get after we do our keep, change, flip. Notice I've already expanded the x plus 3 squared, and I've already taken out the GCF of the 5x and 15. The numerator and denominators both contain a factor of 25, as well as 1x plus 3. Therefore, I can cancel one of each, leaving me with my answer of x plus 3. In 3.2, students will be able to add and subtract rational expressions, and our question is how are adding and subtracting similar to adding and subtracting simple fractions? If our denominators are the same, then adding and subtracting is probably the most simple thing that you'll see in this unit. Similar to 6/10 plus 1/10, which is 7/10, 6x plus x over 10y is going to be 7x over 10y. With subtraction, 6x minus 1/10 is 5/10, leaving us with 1/2. And if I were to subtract my rational expression, I get 6x over 10y minus 1x over 10y. That's 5x over 10y. In other words, 1 over 2 and then x over y, leaving me with x over 2y. 4p minus 3 over 2p plus 7 plus 3p plus 8 over 2p plus 7 means I'm going to combine the numerators and leave the denominator alone, combine my like terms, and get 7p plus 5 over 2p plus 7. Notice, I'm not canceling the 7s or the p's. They're not the same in both my terms because I have a difference of addition. So we need a multiplication term in order to be able to cancel the numerator and the denominator. In the second example, we have 3y minus 6 all over y squared plus 3y minus 10. We can then factor out a GCF from the numerator, and we can factor the denominator. That way we can see that there's a y minus 2 term in both the numerator and the denominator that can cancel, leaving me with our answer of 3 over y plus 5. The bottom example, we have 8y minus 16 all over y minus 2. Factoring out a GCF of 8, we're left with y minus 2 over y minus 2, which can eliminate one another, leaving us with an answer of just 8. To add and subtract with a different denominator is perhaps the hardest thing we'll see in this unit. When the denominator is not the same, we must make it the same by finding the LCD, or least common denominator. 2/5 plus 3/7 can't be added in the same way that 6/10 and 1/10 was. We need to find the least common denominator between 5 and 7. In this case, the least common denominator is 35. So we need to multiply the 2/5 by a fraction 7 over 7, and we need to multiply 3/7 by the fraction 5 over 5. In this way, we can then combine our numerators, 14 and 15, because our numerator is the same, and get our answer of 29 over 35. For rational expressions, the same is true. The least common denominator of 5x and 7y is 35xy, meaning that our left fraction needs to be multiplied by 7y in the numerator and denominator, and our right fraction needs to be multiplied by 5x in the numerator and the denominator. And then we can combine our like terms. 15 over 7z plus 8 over 6z. Both of our denominators already contain a z, so let's just find the least common denominator between 7 and 6, which is 42. Therefore, we need to multiply the left fraction by 6 in the top and bottom, and our right fraction by 7 in the top and bottom, getting us 90 plus 56 all over 42z. We can simplify that fraction to give us our final answer of 73 over 21z. 7 over 2x minus 3 is a little more complicated just because you don't have or you can't see the fraction of -3. But any whole number can be written as a fraction over 1. Therefore, that thing can be rewritten as 7 over 2x minus 3 minus 3 over 1. We need to get a common denominator of 2x minus 3, which means I need to multiply that fraction in the numerator and denominator by 2x minus 3, and then I can combine my like terms, leaving me with 16 minus 6x. If you choose to take out the GCF from there, as you can, you'll notice that nothing cancels, so either form is correct. The right example involves a little bit of factoring. So once we've factored the left fraction and the right fraction, what do we notice is the same in both? Both contain an x plus 2. Therefore, when I find the least common denominator, I already have an x plus 2, but my least common denominator needs to have an x minus 3, an x plus 2, and an x plus 3. So we need to multiply the left fraction by x plus 3 in the numerator and denominator. And we need to multiply the right fraction by x minus 3 in the numerator and denominator. Then we can distribute and combine our like terms into our final answer of x squared plus x plus 3 all over x plus 3, x plus 2 times x minus 3. Here's a more complicated test question. What simplified rational expression is equivalent to x squared minus 4 over x plus 9 minus x plus 6 over x minus 5? Notice all of our answers have the same denominator. That denominator comes from multiplying the left fraction by x minus 5 in the numerator and denominator, and the right fraction by x plus 9 over in the numerator and denominator. Therefore, you need to take x squared minus 4 times x minus 5, and subtract that with x plus 6 times x plus 9, and tell me if you get A, B, C, or D. The correct answer is indeed A, but be sure to know exactly how to do this problem for the future. In subunit 3.3, students will be able to solve rational expressions and understand what an extraneous solution is and why rational expressions have them. A rational equation is an algebraic equation that includes at least one term expressed as a ratio. A rational equation defines a specific relationship between numbers and variables. This relationship can be analyzed to find a solution to the equation. And there are two ways that we solve rational equations. The first is to create a common denominator and then cancel it out. And the second is to cross-multiply. So cross-multiplying should be a review from previous math classes. If I were to cross-multiply x over 4 equals 6 over 8, I would need to multiply 6 times 4 and set it equal to 8 times x, leaving me with 8x equals 24. Then I need to solve for x by dividing both sides by 8, giving me x equals 3. And then lastly, I need to double check that 3/4 is indeed equal to 6/8, which it is. In this second example, rather than solve by cross multiplication, we're going to solve by creating a common denominator and canceling it out. So what's the least common denominator between t, 12, and 3t? Well, the numerical least common denominator would be 12, and the variable, we need at least one t. So our left fraction, 5 over t, needs to be multiplied by 12. Our 3 over 12 needs to be multiplied by t, and our 9 over 3t needs to be multiplied by 4. So on the left-hand side, we've created a new fraction of 60 minus 3t all over 12t. And on the right side, we've multiplied it by 4 to get our new expression of 60 minus 3t over 12t is equal to 36 over 12t. Notice our denominators are the same, so we can cancel them out and focus only on the numerator. 60 minus 3t equals 36. This is a one-step or multi-step equation rather, so we need to subtract 60 on both sides, leaving us with negative 3t equals negative 24, and then divide both sides by negative 3 to get our answer of 8. We lastly need to double check that 5/8 minus 3/12 is equal to 9/24. For this rational equation, again, we're going to focus on the left side. However, rather than cancel out that common denominator, we're going to cross multiply. So we need to first create a common denominator on the left-hand side. 2 over y minus 1 over y plus 2. We need to multiply 2 over y by a factor of y plus 2, and we need to multiply 1 over y plus 2 by a factor of y. Then we can simplify. Now we have y plus 4 over y squared plus 2y is equal to 1/3. So we're going to cross multiply and get 3 times y plus 4 is equal to 1 times y squared plus 2y. We can then distribute, and then we're going to move all of our things onto the right-hand side. So we're going to end up with y squared minus y minus 12. From there, we can factor that into y plus 3y minus 4 and get our solutions as negative 3 and positive 4. We then need to double check that both negative 3 and positive 4 work. In this case, they do. Last example, again, we're going to try and combine to get a common denominator, and we'll notice that our common denominator will in fact cancel in this case. So on the left-hand side, we need our common factor needs to be p minus 4 at times p plus 2. So our left fraction needs to be multiplied by p plus 2 in the numerator and denominator. Our right-hand side needs to be multiplied by p minus 4 in the numerator and the denominator. We then set that equal to 6 over p squared minus 2p minus 8. Factoring that denominator on the right-hand side, we notice that our denominators are in fact the same. So we can cancel out our denominators, leaving us with just p squared minus 3p plus 2 is equal to 6. We then again need to move everything all onto one side and factor to get p minus 4 times p plus 1 equals 0, leaving us with solutions of negative 1 and 4. Our last step, as always, is to double check that both of them work. However, the right-hand side solution, when p equals 4, doesn't work. Why? Where is the issue? If you're looking at 1 over 4 minus 4 and saying that that's the problem, you're correct. 1 over 4 minus 4 becomes 1 over 0, and we know that that's not possible. Therefore, we call that an extraneous solution. An extraneous solution is a solution of an equation that arises during the solving process, but which is not a solution to the original equation. It occurs when the denominator is equal to 0, as in the example before, or the solution results in a value that's irrelevant in the context of the original equation. For example, say you're calculating the distance or time it takes something to happen. It doesn't make sense to have a negative distance or a negative time. Therefore, those, quote, solutions would be labeled extraneous. There are many real-world applications of rational equations, and they can be useful to represent multi-person work problems. Work problems often ask us to calculate how long it will take different people working at different speeds to finish a task. The work formula has 3 versions, each found by simply manipulating the original. Work equals rate times time. If I then want to solve for time, I need to divide both sides by rate. So time equals work divided by rate. And lastly, if I want to solve for rate, I need to divide both sides by time, leaving me with rate equals work over time. So let's take a look at this example. Myra takes 2 hours to plant 500 flower bulbs. That's equivalent to 250 bulbs per hour. Francis takes 3 hours to plant 450 bulbs. In other words, Francis plants 150 bulbs every hour. Working together, how long should it take them to plant 1,500 bulbs? Well, working together, Myra can plant 250, Francis can plant 150. That means that every hour together, they can plant 400 bulbs. So if I want to know how long it would take them to plant 1,500, I can set up that ratio and cross multiply to solve for time. In this case, x equals 3 hours and 45 minutes. This one is an extreme challenge. Kiara and Jamari have a cleaning business. Kiara can clean an office suite in 20 minutes less time than it takes Jamari to do the same job. So if Jamari can clean this suite in X amount of time, Kiara can clean it in X minus 20. Working together, they can complete the job in 120 minutes, or 2 hours. Approximately how long does it take Kiara to complete this job if she works alone? Assume both people work at steady rates and their rates are not affected by working alone or working together. Doing the math, the answer comes out to be C. In the last subunit, 3.4, students will be able to graph rational expressions and be able to determine the rational function's vertical asymptote, horizontal asymptote, holes, as well as the domain and range. So a rational function, again, is a function that has a fraction of the form p of x over q of x, where both the numerator and the denominator are polynomials, and the denominator is not 0. Implied domain is how we refer to the domain of a rational function. It means that our rational function has a domain of everything, all real numbers, except when the denominator is equal to 0. When I factor the bottom of this example, my new function becomes x minus 1 over x plus 1, x minus 2. Therefore, my domain is all real numbers except when the denominator is 0. The denominator is 0 when x equals negative 1 and when x equals 2. Therefore, my domain is all real numbers except those. To find the x-intercept, that's where the function crosses the x-axis, and it means our y-coordinate is 0. To find the y-intercept, which is where the function crosses the y-axis, the x-coordinate is 0. So let's go ahead and practice again to find the x and y-intercepts of this function. To find the x-intercept, we need to set it equal to 0. 0 equals x plus 3 over x minus 2. The only way that it's possible for a fraction to equal 0 is if the numerator is 0. So we don't care about the denominator. We only care about when 0 equals x plus 3. And that's true when x equals negative 3. Therefore, our x-intercept is at negative 3, 0. Our y-intercept is when we plug in 0 for all of our x's. And therefore, we get our y value of being 3 over negative 2. So our y-intercept is 0, negative 3 over 2, or 0, negative 1.5. Vertical asymptotes of a function are invisible vertical lines that the graph is always approaching but that it never touches. They serve as boundaries for the function's graph. To find the vertical asymptote, we set the denominator equal to 0 and solve for x. So those values that were excluded in our domain are actually our vertical asymptotes. However, there's an exception. If a factor in the denominator is the same as the factor in the numerator, they will cancel out, which means that it is not a part of the vertical asymptotes. In this leftmost example, 1 over x minus 4, we need to set the denominator of x minus 4 equal to 0. X minus 4 equals 0 when x equals 4. Therefore, our vertical asymptote is at x equals 4. The vertical asymptote of the rightmost example is actually going to have 2, because when I factor the denominator, I get x plus 1 and x minus 1, which means our vertical asymptotes are at x equals 1 and x equals negative 1. A hole on the graph looks like an open circle. It's where the function approaches but never is actually defined at that point. So to find a hole, you're going to simplify the rational function by factoring and cancel out common factors. If you canceled something out, that is the hole. So that is the x value of the hole. You're going to solve that canceled out portion for x. Then you're going to take that x value and plug it into the simplified form of the equation to get a y value. So let's find the vertical asymptote and holes of the left example. That requires us first factoring the denominator. So we get x minus 5 over 2x minus 3 times x plus 1. Nothing canceled, therefore we have no holes. But our vertical asymptotes are where our denominator equals 0, and we have 2 of those, at 3/2 and at -1. On the right-hand side, again, I need to factor, so I get x plus 1 over x minus 3 times x plus 1. The x plus 1 terms cancel, which means I do have a hole, and I found my location by setting that factor equal to 0. So our vertical asymptote is at 3, and our hole is at x equals -1. So to find the exact point, we need to take -1 and plug it into our simplified equation, and therefore we find that our hole is at -1, -1/4. The horizontal asymptotes of a function are invisible lines of the graph that the function is approaching but never touching. They are identical to the vertical asymptotes, except in this case, they're horizontal. So like vertical asymptotes, horizontal asymptotes serve as boundaries. And to find the horizontal asymptote, we need to compare the degree of the numerator to the denominator. There are 3 possibilities. If the degree in the numerator is equal to that in the denominator, then our horizontal asymptote is our coefficient of the numerator divided by our coefficient of the denominator. If the degree of the numerator is less than the degree of the denominator, then our horizontal asymptote is at y equals 0. And if the degree of the numerator is bigger or greater than the degree of the denominator, then we don't have a horizontal asymptote at all. In the bottom left example, both the numerator and denominator have a degree of 2. Therefore, we need to then look at their coefficients. 4 over 1 simplifies to just 4, so our horizontal asymptote is at y equals 4. In the middle example, the degree in the denominator is larger than the degree in the numerator, therefore our horizontal asymptote is at 0. And in the rightmost example, the numerator has a degree of 4, the denominator has a degree of 2, therefore there is no horizontal asymptote. Looking at the graph, which equation is represented by the graph? Well, I see that there is a vertical asymptote at -1 and a horizontal asymptote at -5. So let's look for our vertical asymptote at -1. Vertical asymptote was where the denominator equaled 0, which means that when I plug in -1, my denominator should be 0. So let's go through our answer choices. Looking at A, when I plug in -1, -1 plus 1 is indeed 0, meaning A is going to be our correct answer. But just to double check, let's go through B, C, and D. -1 minus 1 is -2, not going to be B. -1 minus 2, -3, not going to be 0. And D, -1 plus 2, again, does not equal 0. Therefore, we were correct in saying that our answer was A. In the bottom multiple choice question, where it asks us to find all of the asymptotes, let's first look for the horizontal asymptote by looking at the degree of the numerator and the degree of the denominator. The denominator has a degree of 2, and the numerator has a degree of 1. Therefore, the degree in the denominator is larger than the degree in the numerator, meaning we have a horizontal asymptote at y equals 0. That eliminates options A and D. So now we need to look at our vertical asymptote. Do we have vertical asymptotes at 2 and -2, or do we have vertical asymptotes at 3? Go ahead and pick your answer choice now. If you picked B, you are again correct. Just to recap before or just for review of our test, since we may or may not have done this graphing project at the time you're watching the video, again, our x-intercept is where y equals 0, and we solve for x. Our y-intercept is where x equals 0, and we solve for y. Our holes occur if something cancels. Our horizontal asymptote has 3 possibilities, and our vertical asymptote is when the denominator equals 0. Best of luck in studying rationals.